heat flux that's proportional to the temperature gradient. If you have a larger thermal conductivity, you would have a larger heat flux with the same temperature gradient. Okay? So thermal conductivities are properties of substances. For example, metals typically have a higher thermal conductivity than ceramics. Typically, gas has a very low thermal conductivity. Okay, so these are the things that are a prerequisite in the calculation of energy transports. Okay, so if we want to know the transport of energy, the temperature distribution of specific substances, it's important that we know the thermal conductivity of a particular material or substance. Okay. Now, so this is the 1D form, and we can extend that to a 3D form. So it's fairly straightforward, right? So let's take a look at the 3D form. So 3D form. We have basically the heat flux as a vector equals to the negative of the thermal conductivity with the dot product, or the temperature gradient in 3 dimension. Okay. So this is our Fourier's law of heat conduction. Okay, so now let's take a look at diffusivity, right? As I mentioned that heat and mass transport are similar in a lot of ways, and the first similarity lies in their similar formulation in the heat flux and mass flux, and that's going to be related to their thermal conductivity and diffusivity. So let's take a look at diffusivity. Let's scroll this up a little bit. We're going to stop here maybe. Okay, so diffusivity. So again, let's do that hypothetical experiment again. Okay, so again we have, let's say, a slab. So this, let's say we have a porous silica here. So this is our porous silica. And infinite large slab of porous silica. Also we have, initially we have it being a thickness of L, and initially we have, helium on both sides of our porous silica. So we say we have helium gas here, and we also have helium gas here. So our initial concentration of the helium gas inside this porous silica is going to be uniformly or be constant at some C naught. So C naught, and this is also when we have initial conditions. So T is smaller than 0. Initially everything is at a constant condition. So we're going to use, this is called the diffusion of, oops, what has happened? Where did my blue pen go? Okay, never mind, we can change, always find a new one. Okay, so this is diffusion of helium through porous silica. As an example. Okay, so now at time equals to, let's change better color. So at time equals to 0, at t equals to 0, let's say we suddenly have a change in the condition. So let's say again we have y equals L, y equals 0, we suddenly have a flow of helium. So we have a flow of helium. With concentration, with constant concentration of C1, which is higher than C0. So again, we can anticipate that at time equals 0, at this specific instant, the temperature profile, the concentration profile looks like this. At the bottom surface is C1, at the top surface is C0. Again, we can anticipate the situations at a small t. So the system is now perturbed and it will, respond to the changes. So at small t, we can again anticipate that the concentration might look like this. C1. And again, at steady state, or when t approaches infinite, again, when t approaches infinite, we again can anticipate that the concentration reaches a new equilibrium, and it will be linear. So you can anticipate something like this. So you anticipate a linear relation of the concentration profile across our slab. So at small t, the concentration would be a function, again, of position and time, but when time approaches infinite, the concentration is just a function of position. Okay? So again, at steady state, a constant molar flux of helium flows across the porous silica where it can be described as follows. So the molar flux of helium across the porous silica, so across the cross-sectional area, which we usually use the symbol using J as the molar flux of helium, is actually equal to or proportional to the concentration gradient. So that's delta C over L, and it's proportional by the diffusivity. So the diffusivity of helium in silica. Okay. So again, we can figure out the differential form. So first, let's say helium is species A and silica is species B. The differential form would look like the following. So the differential form we have the diffusivity of, the flux of species A in the y direction equals to the negative of the diffusivity of species A in B times the concentration gradient of species A in a particular direction. Okay, and this would be the 1D Fick's first law of diffusion. So first law of diffusion. Diffusion. Okay, so again, you can see that when a system, for example, when the time is allowed to relax, when the system is allowed to relax for infinite long period of time, it reaches a new steady state. So at a new steady state, there's going to be a constant molar flux of helium across the porous silica. And that can be described as the product between the diffusivity of helium in the silica multiplied by the concentration gradient across the porous silica. Okay, so again, the diffusivity, just like the thermal conductivity, is a measure, or is the coefficient that relates the gradients, either the concentration gradient or temperature gradient, to the heat flux or the mass flux. Okay, and again, for mass transfer, we can also write things in the mass unit. So this is in molar units, but also we can write things in mass units. So just, actually for chemical engineers, we use the molar units more than the mass units, but as an introductory, I think we should also introduce this. So in mass unit, we have slightly different symbol. So JAY equals to basically the mass flow rate over the cross-sectional area, which again equals to negative rho DAB, and which is, instead of using the concentration, we use the mass fraction, dy. So let's maybe use a different color, not to confuse ourselves. Let's use some different color here. Let's maybe use green. Okay. And here, the W sub A here is the solubility of helium in silica, and it's basically a mass fraction. Okay, so again, the important thing here is the diffusivity. So this is our diffusivity, or sometimes we call it diffusion coefficient. Okay. And let's kind of extend our discussion on Fick's first law of diffusion. Okay. So let's take a look at that again. So Fick's first law of diffusion is not as generic as you might wonder or imagine. So let's take a look at what it is. So some notes about Fick's first law of diffusion. So some notes about it is it's only valid for binary systems. Binary solid, binary liquid or gas solution Okay, so it's going to be valid for any binary solid, liquid, or gas solution provided the mass flux of A is the mass or molar flux relative to the mixture velocity. What does that mean? We'll cover that in a second. Mixture velocity. Okay, what does that mean? Okay, so let's say that generally